2022 and 2023. And he is the first audiology scholar in the region of South Asia to receive this prestigious recognition. Without further delay, let's put our hands together to invite Associate Professor Dr. Muhammad Amani Zakaria for his speech.
Okay, Assalamualaikum and good morning to all of you. How are you today? So it's good. Alright, so it's good for me to see many familiar faces. Alright, so some of my students still recognize me after 15 years. Alright, perhaps I'm not that different compared to maybe about 10 years ago. Alright, so okay, we have 2 days to learn audiology. Alright, so in USM RD program, I teach my students 4 years to learn audiology. You need to finish everything in 1.5 years. So 1.5 days, sorry. Okay. So it's a little bit challenging there, right? So most of the knowledge you can get from reading what we call the journals, the books, e-books, websites. Then you can get the knowledge that you want. But sometimes you need to have teachers in order to really understand what is happening. Okay, all right. So okay. That's my email. So I would say that what you call perhaps you will learn something good for the next 2 days. But the most important thing that I think you should ask questions. I'm sure that many of you have questions after reading whatever websites, books. We will make this session interactive. Okay, and also you can contact me at any time. That's my email. If you to ask any questions, right? I will surely read your email, but I'm not sure when to reply then. Don't worry, I will read your email. Don't worry. All right. Okay. All right. So all right. Before I start, I would like to thank Mr. Ranjit for inviting me. Thank you again. All right. So I'm very happy to be here. All right. So I hope that for the next 2 days, the session is going to be beneficial to all of you. And please ask questions. Please ask questions. We'll try our best to entertain your questions. Right. So before I start, I just want to know how many audiologists in the room. All right. So perhaps the topic is going to be quite boring to all of you. All right. And I hope that you're not allergic with the blue background. It's my trademark. Nobody can use this without permission. Right. So ORL specialist. How many of you? All right. MA students or master students? All right. MO? All right. Okay. So for MO in this room, how do you rate your audiology knowledge? From 1 to 10? Okay. 1 is knowledgeable, 10 is very knowledgeable or extremely knowledgeable. Okay, right? Right, okay. Alright, also for master student, right? Okay, the challenge is that in order to have a very good understanding, you need to have some little knowledge about physics. There are some physics elements to make sense what is happening when you read the audiogram, for example. Right? So certain audiogram will show specific pattern, specific to certain disease. Alright? Otitis media efficient, you will expect something like this. Right? Nose exposed audiogram, it will be like this. Right? So that's why we need to talk a little bit about physics. Not so much, just a little bit. Right? So I'll start with that one first. Right? Please let me know if it's actually very boring. Right? I will skip to the next slide. Alright. Okay. Okay. Alright. This is something that you can read from the website. Okay, so first of all, we are talking about sounds. Alright? Hearing problems, whatever this is about people cannot hear speech sounds. So we need to know a little bit what is sound actually. So, alright, sound is part of what we call longitudinal wave, which means that we're talking about medium. Alright? When there is a sound, there will be a displacement of the medium. For example, in this room, it's actually the air medium that is parallel to the direction of the travel. Right? The way the air molecule move when they are sounds are actually different. So longitudinal wave is something like this. There is another wave known as transverse wave. That is the displacement of the medium is perpendicular to the direction of the travel. To show you some. Alright. So this is the transverse wave. Alright. So that is the medium, or just imagine air molecules. It will actually not sound. So that's why the sound is travel from one part to the other part. By like that. Right? So that's the transverse wave. So this is the longitudinal wave. These are sounds. Imagine that's the air molecules that you cannot see in this room. Right? When somebody is, and there's no sound, everybody is quiet, the air molecules will be static, or it will move very slowly. Once somebody is speaking, the air molecules will move because they are sounds. That's how it moves. Alright? Like that. Like that. So you have the two areas, the compression and the rarefactions. You can see that sometimes the air molecules are close to each other, and sometimes it's actually apart from each other. The close one we call it as a rarefactions, and then the compression. Sorry, the far apart ones are the rarefactions. The close one is the compression. These are the sound wave. Alright? Okay. Longitudinal wave. Alright. This is the simplest what we call the definition of the sound, which is the movement of the or disturbance that requires medium. Right? I'm talking in this room, so it's an air medium. There are air molecules that will move when somebody is talking. Right? So not just the air medium, the sounds can also travel through other medium, for example through solids. Right? Right? If the air molecules are closer to each other, the sound transmission is better. Right? For example, this is the example that I've given for many times. If you are in the near the rail track, right? Very long rail track. If you can see about maybe 500 meters away, you cannot see any train. You cannot hear any train. But when you put your ears to the rail track, then you can hear something. Maybe the train is 1 kilometer away. You can hear faster with if the medium is actually solid compared to air. Okay, the same train is coming, but you cannot hear unless it's actually closer. Alright, so sound can travel to many mediums. Alright, but we're talking something that's more relevant is the air medium. Okay, alright. Okay, let's skip that. Okay, little bit some basic about sounds. So we have two types of sound in the world. The first one is the pure tone. Sounds with only one frequency. We use pure tones for testing hearing in our clinic at certain frequencies, right? So pure tone means that you have only one energy. If we do the frequency analysis, it's only one energy. Pure tone 1000 Hz means that it has only 1 kHz energy, right? It's only one frequency. And the next one that's more common is the complex sounds. It can be anything. Space sounds, anything. Complex sounds simply means that it has more than one frequency. Space sounds are complex sounds. Right? It ranges from very low to very high frequency. Okay? Are we okay so far? Alright. And okay, next, sounds can be described in terms of its intensity. How loud is the sound? Whether it's soft, loud or louder. And also the frequency of the sound. Low frequency, mid frequency or high frequency. Okay? This is actually very relevant when we're talking about the audiological assessment later on. Okay? Example pure tone of 1000 Hz. That's why it looks like you have a what called repeatable waveform, a sine wave. Right? So when we measure the spectrum, you can see that here, alright, it's only one energy at 1000 Hz. Okay? No other energy. Right? It's a photon at 1 kHz. Okay? That's the example of the speed sounds. Very easy. No, there are many free software that you can just download. You can just record your voice. Okay? That's how it looks like when you record your voice. Right? When you do the spectrum analysis, you can see that you have lots of energy from the very low frequency to very high frequency. Right? These are complex sounds. So many energies. Not one like pure elementary. Sorry, so like pure tone. Okay, this is another example of the white noise. You can see that you have flat spectrum. Flat spectrum. Okay, it has equal energy at all frequencies. Alright, this is another example. Alright, of the narrowband noise centered at 4 kHz. Right, noise. All of noise are actually complex sounds. Alright, so you can see that it has one peak here. This is the narrowband noise. Centered at 4 kHz. So it's actually 4 kHz is the center, but it also has energy next to the 4K. Alright? So just some example there. Okay, alright. Narrowband noise we use as a masker in pure PTA masking. Right? You know when we do PTA, sometimes we need to do masking. In fact, most of the time we need to do masking. We need to give the masker or the masking noise. This is example of very good masking noise. During PTA testing. Right? Okay, just some basic knowledge there. So this is something that you can easily get from the website. So as a human, you can hear from 20 to 20,000 Hz. Right? And then, alright, frequency is defined as 1/T. Okay? In hertz, right, or per second. So one is actually defined as a 1 complete cycle per second, which means that that's the pure tone, right, or the sound wave. You just look at 1 cycle, what is the duration, and then you can calculate. Then you can easily get the frequency. I show some example. Okay, even though humans can hear from 20 to 20,000 Hz, but our sensitivity is not the same. It's not a flat line. You can hear 20 Hz sound, right? 20,000 Hz you can hear, but the sensitivity is different. Okay, as you can see here. Okay, all right. Okay, so this is 20,000 Hz. So this is the low limit of hearing, which is the hearing threshold. This is actually the hearing threshold, and this is the upper limit of hearing. Above that, you feel uncomfortable. It's too loud, and it can even rupture your TM. All right. So this is the intensity in dB SPL. dB sound pressure level SPL, not dB HL, the one that we use on audiogram. No. So this is the frequency. That's what it looks like. The hearing threshold, right? So 0 is the one that is very familiar, or it's the lowest sound that we can hear. So you can see here, this is where your hearing is the most sensitive, around here, which is around 0. Means that, for example, at here at 3K, your hearing threshold is 0 dB SPL. This is the best hearing level that you can get. But higher or lower than that, it becomes less sensitive. For example, even though you can hear 20 Hz sound, you can hear, but it has to be around 80 dB. Then you can hear it. Below that, you cannot hear. We are not that sensitive to certain sounds, even though we can hear that. Right? So it's like that. That's how the curve looks like. Right? In PTA, what is the lowest frequency that we use? Berapa? 250 too. Alright, what is the highest? 8K. So this is 250, this is 8K. Can you see that this is the lowest reading that we can get? It's the best reading. Why we do not test at 20 Hz? Right? Why we do not test at 20 Hz? because our threshold is actually very high. Right? In fact, when talking about the speed sounds, you don't need 20 Hz. Right? Or 200 and above is good enough for you to hear speed sounds. Right? So that's how it looks like about our hearing ability or our hearing threshold in dB/SPL. Right? So you can see there's like a curve there. Right? When doing Pearson audiometry testing and you report your you plot your audiograms on the audiogram, sorry, and it's actually in dB what? dB/SPL or dB/SPL? SL. But this actually in dB/SPL. What is the relation? Who knows? I belajar makan tengah hari dekat sini. Because the original measurement of the hearing is actually in dB/SPL. This is actually from 1950s graph. The dB/SPL comes later. Who knows why is that? We use dB/SPL when we plot our graph. Sorry. Okay. Alright. Human ear, but they actually come from human as well. Okay. Okay. Actually, the reason is going to disappoint you, right? Because another reason when we do hearing test for babies, dissection test. Siapa pernah buat dissection test dekat sini? You guna apa to deliver the stimulus? You guna apa? No, dissection test kita tak guna speaker. VRA kita guna speaker. Kita guna apa? You akan tengok tak orang buat dissection test? Pernah tengok tak? Alright, kita ada baby, duduk atas mom's lap. Alright, and then there is a tester at the back, 45 degree bagi bunyi. It can be, you actually boleh guna your own voice, ataupun you boleh guna noise maker, right? So kalau you use your own voice, high frequency for example, we expect the chair to turn to the tester side lah. Turn means that the chair can hear sounds, right? And how do we measure our stimulus level, our voice? Kita guna apa? Yes, we use sound level meter because this test is actually very simple. You do not use audiometer for that. You use your own voice, alright? And then you need to have sound level meter which records sound levels in dB/SPL, not dB/SPL, alright? But we still use dissection test. We still record the sound in dB/SPL because there is no other option. So which means that there is nothing wrong to use dB/SPL to describe our hearing test results. No problem at all. Tak ada masalah pun. That's why for babies we do dissection test. We use sound level meter to actually come up or diagnose the hearing level, for example. Kan? But why in PTA kita boleh dB/SPL? Tahu kan? Who knows? Yes, betul. It's good. It's all about you. If you can see here, it's actually they are curved there. It hurts eyes a lot. Itu masalah dia. Right? They just fikir, this doesn't look good. How to make it flat? They convert it to dB/SPL. That's the reason. First reason actually. Right? They just want to have a flat response from the when you do PTA, if you record in dB/SPL, you can still get quite good result, but it actually have a curve like this, right? I mean, it's actually reverse because it's actually 0, 140. In PTA, it's 0 up, 120 down. So it's actually mirror effect. It will be like that, like that, right? But there's nothing wrong. Sometimes we do record hearing test results in dB/SPL. For example, when we test babies. Okay, both can be used actually. Except that now as a standard in any audiogram or any PTA testing, it is plotted in dB/SPL. Okay, first reason they want to make it a straight line. it's not what we call, the reason is not really scientific. It's about mata you sakit tengok aerogram sampai you tak tidur malam. Apa salah ada tu mengganggu emosi. Alright. So it's not physiological at all. There's no physiological reason there. Right. The second reason why we want to convert into DBHL because we want to match with the bone conduction results. Also in DBHL. Right? I'll talk about the bone conduction later on, but you know that when we do bone conduction testing, we use the bone vibrator, right? We place on the mastoid, kan? Betul? And the bone vibrator, because the way it gives sound is through vibration. So the calibration unit, okay, or the way we design the bone vibrator or its output, it's not in DBHL. It's actually vibration, it's in force level. Okay? So in order to match between AC and BC on the same audiogram, both should be in DBHL. Because we need to have both, for example, to detect the airborne gaps. Something like that. So they should be in the same unit. Alright? Boleh? Alright. Ada soalan ke? Okay, good. Okay, another very simple physics. So we have the low frequency sounds. Alright? And also high frequency sound. What are the differences? Except the color. Okay. What are the differences between low frequency and high frequency sounds in terms of the wave? Wavelength. Okay. So which one is longer, which one is shorter? Alright. So the longer will be the lower frequency. Okay. And high frequency has a shorter wavelength. Right. Why is this important? Alright. When you do PTA testing, you are delivering this kind of sound, Kirtan or the sine wave, high and low frequencies, and we want to see whether this sound is can enter the external ear, can enter the middle ear, can enter the inner ear properly or not. We want to we want to see is the sound transmission whether it's okay or not. If everything is okay, the sound can travel from the external ear to the inner ear in a very good way, so you have normal hearing. Nothing wrong there. What if there's a blockage in the external ear canal? Right? There's a very big earwax. How do these sounds react when they are obstacle in the external ear canal? So that's why the wavelength now is actually very important. Or if on the tympanic membrane you have perforation, 10%, 20%. So what happened to the sound? Where does it go? Right? Which one has the advantage and so on? This is something that is why the wavelength is actually very important. Right? We will go to the specific condition later on, but just one message from me is that because of the very long wavelength of the low frequency or longer wavelength, it has a better bending ability. Which means that when you have earwax, maybe partially closed, there are some holes there. The source that can go through is actually low frequency. Right? Longer wavelength gives low frequency a better bending ability. Low frequency knows how to find the hole. Right? If there's more hole, they know how to find the hole, but not high frequency. Right? Which means that if you are still with me, alright, when there is a partial blockage of the external ear canal due to wax occlusion or whatever, you expect to have high ke low frequency hearing loss? High, yes, betul. Because the low frequency, dia nampak lubang sikit, dia boleh masuk and then it can reach the TM safely without any attenuation. But high frequency cannot do that. So you expect high frequency conductive hearing loss, high frequency airborne gap in the case of partial wax occlusion. Make sense tak? Make sense, eh? Boleh, eh? Because we're talking about conductive hearing loss, it's quite rare to have high frequency airborne gap, eh? Most of the airborne gap will be at low frequency or the mixture. To have a pure airborne gap at high frequency is actually quite rare. We can get, for example, in the case of partial wax occlusion. Right? The same thing. when you have, if the external canal is good, no obstruction or no obstacle there. But what if you have perforation on TM? Maybe 30% perforation. Okay, of course, some sounds can escape in to the middle ear instead of hitting the TM. Right? What sounds that will escape? Low ke high? Low ke high? Yes. Because if there are holes there, low frequency is actually very good in finding the holes. So you punya hearing loss, low frequency ke high frequency? Ya ke? Low ke? Kenapa low? Faham ke? Yang tadi, when you have a partial waves of ocean, you don't have extended loss because low can go through. Now, if you have a TM compression, alright, the low frequency can go through to the middle ear, and then you will have low frequency hearing loss. Ke high frequency? Okay, alright. Siapa cakap high frequency jadi? Alright. Low ke high? Kenapa low? Nampak confident je? Kenapa low frequency? Why low? Sebab the sound can escape through the hole, then dia reach the what we call the oval and round window kan, directly without using the optical. Why is that? You expect low frequency loss rather than high frequency. Okay, alright. Why low? Why low frequency? Alright, okay. Ataupun why high frequency? Siapa cakap high frequency ni? Dia balik batu, dia sembunyi tangan okay. Kenapa high? Are you thinking that because the sound can go through the TM, it will amplify more high, the vibration of the low frequency is not affected? Macam tu ke? Macam tu? Alright. Okay, they're actually very simple. I will go to the physiology of hearing in a few minutes, but many of you has good knowledge about the anatomy book, so you need to know the ossicles is the most important mechanism to transmit sound from the external ear to the cochlea, right? We use the ossicle, that's why we have the ossicles, right? So remember that. I know that some of you might be confused. What happens if you have no ossicles? Alright, TM ada, ossicle tak ada, two windows tu ada. Can the sound go through the cochlea or not? Without the ossicle? Boleh ke tak boleh? Boleh? Kan? Boleh? But what is the problem? Kalau you tak ada ossicle, no ossicle, sorry? Huh? Alright. First, you lose the amplification because there are no ossicle kan. You know from the textbook, the ossicles or as a whole, the middle ear transformer action, when amplifier sound is around 30 or 32 dB. You know the area ratio, the size of the TM compared to the round window is about 7 times larger. So it will increase the sound by the sound pressure level at the time it reach the over window. And the level ratio, the length of the header of Melius, it's about 1.3 times higher than the length of the incus. And also the TM Buckley effect. When we add together, you have the around 32 dB in the transformer action. Of course, when you have no ossicle, no amplification. But not just that. Not just that. I'm sure that you have read somewhere about the round window baffle effect. Pernah dengar? Macam pernah dengar kan? Do you know what is that? You know what is raw window Bedford effect? Alright, so it's very easy. I'll show some figures. The way cochlea is stimulated, okay, is when if the sound, for example, if you have ossicle, if the ossicle is pushing the over window inward, the round window will be upward, right? It's an antagonist action. That's how you produce the cochlear wave movement, and you get the traveling wave, right? So it will go like that, and inward, upward, inward, upward. That's how we stimulate the cochlea, right? So just imagine if you have no ossicle, right? The sound will reach over window and around window at the same time. Boleh imagine kan? I'll show some figure ni. Just nak bagi introduction. Yang nampak macam tak berapa introduction. Right? So tak apa. I will enhance as we go along. But yang paling penting tanya soalan, please ask me questions. Right? So just imagine if there are no ossicle, the sound will reach over window and around window at the same time. The transmission that we call acoustic pathway or acoustic coupling. Kalau ada ossicle, kita panggil ossicular coupling. Right? Okay, so if you imagine if they arrive to the over window and around window at the same time, it will be both will be inward. If both inward, do we have or not cochlear stimulation? The answer is no. So there will be another cancellation. Another cancellation. Right? You lose already 32 dB because there is no ossicle. Right? But you lose another around maybe 30 dB because of the round window Bedford effect. Boleh faham kan? Alright. So when we go back, kita go back to asal. Alright. I was asking whether it's low ke high. Bila you ada lubang kan, you ada perforation on the TM. Alright. If you have seen these cases in your clinic, surely that you can see it's actually low frequency loss kan. You have abundant agak low frequency. Cumanya some student dia tak faham, or some candidates tak faham, because kalau you kata earwax occlusion, the sound low frequency can go through, so you have normal low frequency, high frequency in abnormal kan. But when we're talking about the TM perforation issue, they start to get confused when I say that it is low, it's a low frequency corrective loss. Right? Senang je. The explanation is that, remember, when the perforation is actually very small, we are still using the ossicle as a way to deliver the sound from the external ear to the inner ear. We're using ossicle. Right? So which means that, just imagine high frequency. Let's imagine high frequency. When the high frequency sound reach the TM and they are 30% whole, high frequency dia tak tahu ada hole. Dia tak tahu. So nothing happen. So it will hit the TM maximally. So you have the greatest vibration of the ossicular chain, and you've got good high frequency threshold. As there are no vibration. Sorry, there are no perforation, sorry. Because they cannot see any holes. So you can get normal high frequency audiogram as there are no holes, because there is no escaping. Right? When we're talking about to maximize the vibrations of the ossicle, we need the maximum vibration from the tympanic membrane. When the TM move maximally, then you get maximum vibration of the ossicles, then you can get normal hearing. Boleh faham kan? So that's why high frequency is normal. Right? But for the low frequency, because there are holes there, maybe 30% will escape, go through the middle ear. But unfortunately, nothing happened in the middle ear. Nothing happened in the middle ear. Right? So it will not disturb a lot about the things that I said to you earlier. But the problem is that if you have 30%, 30% perforation, so only 70% low frequency is hitting the TM. So you lose the 30%. So you will have lesser vibrations of the ossicle because the TM does not move maximally. So you get loss at low frequencies. Boleh faham kan? So we are talking about the dominant sound transmission is through ossicle. Right? right? When the size of formation become higher and higher, or bigger and bigger, then you can start to have, hypoxic loss as well. Because some of the hypoxic will also escape to the middle ear. Right? Faham, eh? So, if I can summarize, we're talking about the wavelength issue. It can be advantageous to the low frequency, but it also can be disadvantage to the low frequency. Right? If there's a wax occlusion, yes, good. You can get good, low frequency threshold. Because if there are small holes, they can find the hole and reach the TM safely. So you got good low frequency threshold. But high frequency is not good. It will be blocked. Then you have high frequency corrective hearing loss in the case of partial wax occlusion. When we're talking about TM portion, now it becomes different. It's actually reverse. Right? Having the long wavelength is actually not a disadvantage. Right? Boleh faham ke? Are we okay with that? Okay. Okay. I'll show some diagram later on, and I emphasize this issue again. Okay. Right. Okay, I will make it simpler. I will make it simpler. So, as I showed to you to the diagram before, the hearing threshold tadi, yang ada curve tadi, right? So, measurement, the basic measurement is dB SPL, dB sound pressure level, right? If you download free sound level meter from your phone, from any apps, choose the free one, right? And then when you have the sound meter, if you try to speak, then you can see the meter is working well. Then it will give you certain decibel of your voice. It's actually in dB SPL. Remember that. It's actually in dB SPL, dB sound pressure level, which is the standard measurement of any sound level, right? If we do noise, noise assessment or noise level monitoring in any factories, we also use the sound meter. They will give the result in dB SPL, right? Except that dB SPL has another variation, dBA, dBB, dBC, but it's actually under category dB SPL, right? 60 dB, 70 dB. My voice is about 70 dB, and it becomes 80 dB when I'm very emotional, right? Okay, right? So it's in dB SPL, which is the best way or the most convenient way to record your voice level. Okay, but historically, when we're talking about how do we measure the intensity of the sound or the loudness of the sound, we start with the Pascal. Right? Pascal is the basic measurement of the sound pressure. So, in this room we have the air molecules, and when I'm talking, the air molecules move. Right? If I'm quiet, the air molecules will be static because there are no sounds. Right? So, the Pascal is where you compare, the two conditions when the air molecules are static, when nobody is talking. And then you compare with somebody is talking, and then you've got what we call the intersample of that sound by using Pascal unit. Okay, Pascal is the most basic sound pressure unit. Right? We start with the Pascal first. Right? Except that you might want to think, why is that we do not use Pascal to express, the hearing level for our patients? 60 dBHL, moderate hearing loss. Kan? You are very familiar with that. Why don't we use Pascal? Ada masalah Dia ada masalah kalau kita guna Pascal Okay. That's the dB SPL, our standard measurement. This is the Pascal. This is the Pascal. What's wrong with the Pascal? The numbers are not friendly. Are not friendly at all. Alright? So for example, normal conversational voice is about 60 dB SPL. Very easy to remember. But when we convert into Pascal, 0.02 Pascal. Right? The number is not friendly at all. When the sound becomes softer and softer, for example, threshold of hearing is 0 dB SPL, normal hearing. Alright, normal threshold. But in Pascal is 0.00002 decapascal. Right? Sorry, Pascal. Right? It's too small. It's too small to remember. But again, Pascal is the basic unit to measure sound intensity, but it is not friendly to be used. Correct? In order to do that, we just do the mathematical conversion, as easy as that. Right? Thank you to the previous scientists. They come up with the formula, okay? How to convert sound pressure, basic one, in Pascal, into sound pressure level in decibel. So they come up with the formula very easy. It's a two-way conversion. You can easily convert from Pascal into dBHPL and vice versa. Just a formula there. Conversion. Macam 1 meter equal to how many centimeter? Sorry, I tak ingat Alright. So, yang ni I ingat. So, but it's a simple conversion. That's it. So, we still use the concept of Pascal in our measurement, but we just convert using a simple formula to make it in, we just call it sound pressure level in decibel using some logarithmic function. Right? So, this is some example. You can just go to this website. You just masuk the value, then you can get whatever Pascal or whatever you want. So if I put 60 dB, automatically you have 0.02 Pascal there. Right? It's a simple mathematical conversion, no trick, direct. Right? No trick. So this is the relation between Pascal and dBHPL. Why dBHPL? To make our life easier. Right? Right? So that when we explain the result to the patient, it sounds nice. 0, 10, 20, it sounds nice and logical and easy to remember as well. Okay? Are you okay with this? Alright. Okay. Alright. You know dBHPL. Right? dBHPL comes directly from the Pascal, so there's no problem with dBHPL. Right? But there are another 2 dB, dBHL. Right? Very important. This is the one that we use in our clinics to diagnose hearing. For bone connection and air connection is dBHL. So like what I said to you, why we use dBHL just to flatten the audiogram. Alright? And also we want to come up with a standard measurement unit so that we can compare air and bone on the same audiogram. Alright? Okay. Okay, there is another dB. Another dB. There are 3 dB, dBHPL, dBHL, and dBSL, sensation level. Sensation level. Alright? Which is to me quite important juga sebenarnya. Alright? So what is dB sensation level? It's actually very simple. It's actually whatever intensity that you give above hearing threshold. For example, if you present stimulus at 50 dB, but the threshold of the patients is actually 10 dB. We know later after that. So you are giving 50 dB, it's actually 40 dB above 10, so it's actually 40 dB SL. Boleh faham kan? Alright. Pagi-pagi dah belajar maths kan? Satu hal pula. Alright. Okay. Kenapa you kena tahu? Kenapa this measurement is also quite important in your life and my life as well? Okay. It's very simple. Tomorrow you will learn about non-organic hearing loss kan? Some patient they come to see us with hidden agenda kan? You do not know. Last kali suruh sign form untuk claim insurance whatever kan? Dah mau you tahu tapi dah terlambat kan? Something like that for example kan? So as an audiologist and also as an oral specialist, we need to have good tests to identify the patient that may fall under category non-organic hearing loss. Means that some of them can be malingering, they have normal hearing but they fake that they have hearing loss. Right? They will come and say, okay, I have hearing loss. Then they start to, to play along and then masa buat PT itu you stress, asyik tak dapat hearing threshold. Kejap 60, kejap 80 kan? Alright. I pernah test, pernah jumpa nak hearing loss kadang nak umur 6 tahun. Right, senang betul. Budak 6 tahun pun boleh tipu I. I spend 1.5 minutes, 1.5 hours nak dapat the real threshold. Tak dapat juga, kan? Budak 6 tahun pun boleh tipu you. So hati-hati. So what I want to say is that we need to have extra tests, additional tests that will be covered tomorrow about how can we identify those with non-occurring inner loss. Children are even more difficult because when you found that this child is married clean or faking that they've been lost, it's very hard to convince the parents of. Then they start saying, how do you know that you are right? They start to question, you belajar kat mana? Semua sekali. Pengalaman kerja berapa? Kan? No. Because they first reaction is that they feel that their child is actually very honest. Itu masalah. But that is our problem tomorrow, not today. Okay. So, I think today we will cover acoustic reflex. Acoustic reflex measurement. Right? Who are familiar with acoustic reflex? It's part of the tympanometry. If you have tympanometry machine to measure the tympanic movement, you've got type A, type B, whatever. We also have the acoustic reflex option to record acoustic reflex threshold. We want to see if we give loud sound, whether your stapedius muscle contract or not. If contract means that everything is good. If the stapedius muscle doesn't contract, means that maybe there is a fluid in the middle ear, maybe there's a cochlear damage. You give 100 dB, nothing happens because the cochlea is damaged. And we will record ART, acoustic reflex threshold. Right? So, if you have normal hearing, if I do acoustic reflex testing on you, your threshold will fall between 70 and 100 dB. Means that normal lah tu. If your acoustic reflex threshold is 80 dB, then you are normal. Right? If your acoustic reflex threshold is absent or elevated, 105 dB, so it's abnormal. But we do that, like me myself in USM, I do that on a regular basis. Right? So if you are normal hearing, we expect acoustic reflex threshold around 60 dB above. If your hearing threshold is 10 dB, right? Of course, I can do acoustic reflex on you. I expect it's around 70 dB or 75 dB, your acoustic reflex threshold. So if you go to SL, right? So if your hearing threshold is 10 dB and your acoustic reflex threshold is 80 dB, right? So it's actually 70 dB above your hearing threshold. Betul? 10, 70, 80. Right? So that's the expectation from a normal person. Right? And memang acoustic reflex threshold is always higher than your hearing threshold. Betul tak? It has to be very loud or you contract. So you can have 10 dB threshold, 80 dB acoustic reflex threshold, very logical. Right? Other case, hearing threshold 90 dB, profound. Acoustic reflex threshold 80 dB. Logik tak? Kan lain macam tu. Alright. Nanti actually case managing. Or you can have hearing threshold 70 dB, acoustic reflex threshold 80 dB. It's only 10 dB above. So it's not logical at all. Okay? Right? So this is where we use the sensation level to explain the results. Okay, alright? Okay. I'm not trying to hypnotize you. Alright, so boleh ke you nak break? Boleh ke? Betul ke? Nampak macam dah terseksa ni? So far, any question or not? Ada soalan tak? Okay, I want to touch the last part of physics, but I think it's important for you to know, because we're talking about vibrating object. Alright? Ossicles, for example, ossicle TM or even accidental canal, they vibrate Correct. When the ultrasonds, they vibrate. So you need some basic knowledge about this vibration object. So that's why I try to cover this one, the last one. And then we can have maybe some short break. Alright. So imagine this pendulum that is moving freely. Alright. So with this pendulum has certain length, maybe 1 meter, whatever length, and also the mass, bulat, right? The kg of the system, right? So you can see that it moves now based on the dedicated length and the mass. Betul? Kan? Alright. So it moves. Alright. You can actually measure the frequency of this pendulum. It's very easy. If you are the stopwatch, right? So you go for one full cycle. Now, stop. Okay. Now, stop. One full cycle. Then you can easily measure the frequency of that pendulum. Right? Very easy. For example, I give some example. Maybe 100 Hz. Just one number. Right? So when it's actually simple formula, F equal to 1/T. So you just figure what is the duration for that one full cycle tadi. You bagi, just divide by whatever duration tadi. You've got 100 Hz. Alright? So that is the frequency of this pendulum, 100 Hz, with this kind of length, this kind of mass, or the kg. Okay? Right. So what happens if we do some modification? For example, we use a bigger mass, bola yang lebih besar. What happen? Then we try to move that again. What happen? What happen to the movement? Slow, alright? Okay, but we have to agree the movement will be different, right? Kan sama macam ni juga? Tak, betul. So first we have to agree the movement will not be the same. Yang ni, frekuensi 100 Hz, right? When you start to modify dia punya properties, for example, you add the mass. Surely the movement is now changed. It's no longer 100 Hz, right? Betul? It can be other than that. So the next question, whether it become higher or lower frequency? Higher or lower frequency? Okay. Right. Tahu ke tak tahu? Alright. Okay, alright. I'll show you some simulation. Alright. Okay. Good in mind? Okay? Alright. So So this is two spring system that has certain tension. tension, and also with the weight of 100 gram, right? Alright. So they should move about the same. Sorry, they not synchronized, but they will move with the same frequency, right? They have the same tension, right, or compliance, spring, right, and also the same mass, 100 kg, 100 grams. Sorry. So what happened when we increase the mass? Okay, now we increase the mass. Okay. What can you see? So the movement is slower. So it will go down, up, very slow. Right? So when if you use your stopwatch, it will give you higher duration. From one place to another place is actually a very long time. So if you divide them, you will have higher or lower frequency? Lower frequency. So now it changed from whatever 100 hertz, maybe it becomes 50 hertz. Alright? Right. So because I will try to relate with the middle ear system in a few minutes. We're talking about vibrating object. If you have, object that vibrates at its own resonant frequency, the natural frequency, 100 hertz. When you do the modification, you do something. In this example, you increase the mass. Of course, the movement is now different. That is something that we need to accept first. The movement is no longer the same. The resonant frequency confirm dah lain. Because you do something on the system. Alright? So, but then the issue, okay, now we increase the mass, whether it's giving you higher resonant frequency or lower resonant frequency. The answer is lower. Kalau you faham ini, we have another factor, the stiffness property. Ini mass, stiffness, the tension, right? So kalau you faham itu, then it will be easier to understand about the stiffness. But dia terbalik, which means that when you increase stiffness, it will increase resonant frequency, right? So let me show you. Okay, it's the same mass, but now I make it stiffer. Okay, alright. So if we can. Okay, nampak kan? Right. Right. If we measure, the resonant frequency is actually higher. It's faster from one place to another place. Right? Then you will get maybe 150 hertz resonant frequency. The resonant frequency now change. Now it becomes much higher. Right? Boleh faham kan? Alright. So why is this relevant? Let's talk about the middle ear. Middle ear is also a vibrating object, which means that it is influenced by the mass and stiffness property of the middle ear. Alright, let's talk about mass. Normal middle ear. Which part of the middle ear that contribute to the mass? Okay, ossicles. It gives the mass. The kg, ossicle, right? Ossicle will give the mass. What about the stiffness? Which part of the middle ear that contribute to the stiffness of the middle ear? TM, good. Tiga minit lagi. Lagi? Apa dia? Ossicle tu. Alright. We have the ligament attached, between the ossicle. Of course, ossicle also give the stiffness contribution to the middle ear. Ada lagi tak? Ke cukup dah? Cukup? Audiologist, ada lagi tak? You have TM that will vibrate, of course. Anything that will vibrate itu will contribute to stiffness as well. Lagi? Ossicles, ada lagi tak? Apa dia? Overwindow? Overwindow? Lain macam jawapan dia. Tak salah, cuma lain macam. Alright, so okay. Ada lagi tak? Ada lagi tak? Alright, ada lagi satu, but unfortunately not many people emphasize. Is the volume of the middle ear. Volume of the middle ear. There are three parts of contributors for the stiffness property of the middle ear. The TM movement, right? The ossicular movement with the help of the nearby ligaments, and lastly the middle ear volume, which means that, right? Which means that you tend to have more loss if you have a smaller middle ear volume. Alright? Tulis dulu, nanti I explain. Okay, so macam ni. Alright. When you look at that pendulum tadi, alright, it will move at natural frequency kan? Betul? What is the natural frequency of the middle ear? Pendulum itu wahat atas. We're talking about normal middle ear. What are the, what is the resonant frequency for the middle ear? Berapa? 2K. Alright. Ada lagi? 2K. Semua setuju kan dengan 2K? Setuju? Kenapa 2K? Kenapa 2K? Who knows? Anybody familiar with the wideband tympanometry? Or any of you who is using wideband tympanometry in your clinical practice? Ada kan? Alright. Okay, alright. Tak apa? Tak apa, okay. Jangan rasa bersalah. Alright. Okay. Dia macam ni The middle ear resonant frequency ni dia bergantung kepada how do you stimulate the middle ear. Unfortunately, when your friends over there stating is 2K, confidently, betul lah tu. If you use bone conduction to stimulate the middle ear, boleh faham tak? So 2K is actually the middle ear resonance when you use bone conduction pathway, right? But when you use air conduction, okay, the typical route sounds travel to the middle ear is actually around 1K. 1 kilohertz. That is the resonant frequency of the middle ear by air conduction. So which means that when you have middle ear resonance of 1K, this is the normal frequency of the healthy middle ear. Alright? Okay? So what happens if you have increased mass? Example lah, you see a patient, you do the otoscopic examination, you see there is a quite big amount of wax attached to the TM. Pernah jumpa tak? Pernah kan? So what kind of loss that you will expect? What kind of audiogram that you will expect? So what happened to the overall middle ear system? Macam mana? Oh, it's not affected. Affected ke tak? Affected kan? Okay. So what happened? Ada wax attached to the TM, which means that you have now increased mass. Your middle ear is having increased mass. So from the pendulum tadi, what happened? kalau dia increase mass? Macam mana? Okay, what happened to the resonant frequency when you have increased mass? It will lower kan, betul? So the original is 1000 Hz. When you have middle ear problem, yang macam case, the earwax attached to the TM, then you will get the resonant frequency of course dah change. You buang earwax, dia pergi balik ke normal. Alright? So in theory, that will increase the mass. So the resonant frequency now become lower. Means that your best frequency now it becomes lower. Means that you tak expect ada low frequency loss. Boleh faham kan? You will never get low frequency loss because of the resonant frequency dah bias ke low frequency. The sum of low frequency is actually very good. But you will expect high frequency conductive loss. Boleh faham kan? Because the resonant frequency dah pergi ke bawah, become lower, your sound transmission at low frequency tu okay. But now the high frequency will have hearing loss. So you will expect high frequency conductive hearing loss. Alright, in the case of increased mass. Contohnya ni, earwax attached to the TM. Dulu I suka bagi example otosclerosis, kan? So otosclerosis, you have the bony growth dekat stapes plate kan. Overall, you can imagine the kg become higher. You know, the mass become higher. Betul? Kan? Of course, you get high frequency conductive loss. Cumanya, in the case of otosclerosis, annular ligament yang kena dulu. Kan? Sebab tu you dapat stiffness. Dia rosak kat low frequency dulu. High frequency tu kemudian, maybe after many years, when the kg become higher and higher, then you get low, you get high. Boleh faham kan? Okay? Alright, so remember, when the middle ear system is affected by any pathology, you want to know whether it's increased mass, increased stiffness, ataupun both. Most of the time, you can see in your case actually both lah. You have the low frequency loss, high frequency loss kan? Means that both stiffness and mass is affected. Alright, okay. Earlier, we were talking that most of the cases with conductive loss is actually low frequency kan? Betul tak? Kan? Alright. Alright. Okay. It's actually low frequency, right? Kan? So they're rising. Loss more at low. High pun mungkin ada, mungkin tak ada. So kenapa banyak low? Because go back to the point that I said to you earlier. The stiffness contributors are 3. Mass cuma 1 je. So when imagine there is a fluid in the middle ear, dah sampai ambuh apa ke, 3 benda yang berlaku. First, TM cannot move properly, right? Yes, because of the fluid. Right? Secondly, ossicle cannot move properly because of the fluid. Then apa lagi? Yes, middle ear volume will become smaller. Then you have a very strong low frequency loss. With the case of otitis media with effusion, for example. Right? Okay? Boleh kan? Alright. So, so I think that should be it for this morning. So I think we're going to have some tea break. So kita jumpa lagi lepas ni. Alright, thank you.
Ladies and gentlemen, now we're having a short tea break time. I would like to invite our speaker and attendants to have some light refreshment which is provided outside the hall. Our break time will be till 10 a.m. Please help yourself. We will be grateful if all of us can keep on time for our next session at 10 a.m.